The talk that I want to give you today, my talk's only about 10 or 15 minutes. It's just to give you a flavor of some of the things that are important to what we're working on at the moment here at EPCC, and some of the things that you'll be learning about in the master's program. I've entitled it From Exascale to Smartphones and Back. So I will try to explain as I go along what I mean by this and why both of those things are relevant to parallel computing. So I'm going to start with a graph. I'll explain what all these words and numbers mean, so don't worry if they're not familiar to you at the moment. But I just wanted to give you a feel for the speed at which this field is moving. What we have here is a graph from the top 500. So every year, in fact twice a year, there is a list published of the 500 fastest supercomputers in the world. And what you can see on this graph, on the y-axis, the vertical axis, is the speed of the computer measured in flops, which are floating point operations per second. That basically just means the number of additions or multiplications, the most elementary kind of mathematical operation. How many can it do every second? It's actually a logarithmic scale, which means that as you move up each line on this graph, it counts for a factor of 10. So each horizontal line on this graph, as you go up, the computers are getting 10 times faster. And you can see that, so the middle line, the red line, shows the speed of the fastest supercomputer in the world as it has changed since they started compiling this list in the early 1990s, going right up to today. And you can see that it's followed this dotted line really quite closely. You sometimes hear this referred to as Moore's law. There's possibly a little bit more to it than that, but it basically amounts to the fact that the performance of these computers pretty much doubles every 18 months to 2 years. And you can see that the same is true of the number 1 computer, which is shown in red, the dotted line in the middle, and the number 500 computers. So the bottom one in the list is also following almost an identical trend, just a little bit slower, a little bit further behind. And the blue line at the top is the sum of the total power of the top 500 supercomputers in the world, and it also follows this same trend. So you can see that year on year, computers are getting faster and faster at a staggering rate. And at the moment, we're up to about the 10 petaflop mark. And the extrapolation suggests that we will be up at the exaflop mark. That means 10 to the power 15 operations per second. That's 10 million billion operations per second, if I've got that right. 10 million billion, I think. So these are very fast computers indeed, and the speed at which they're growing is astounding. And one of the things that we're facing, and some of our projects at the moment at EPCC are looking into how we can get ready for these computers of tomorrow. So it's not just a matter of, as you'll see, of taking the same program and running it on a bigger computer. We actually have to think about the changes that we might make to the ways that we write programs so that they can run on these huge computers. So I mentioned there were certain changes about the way that high-performance computing is going. There are various different graphs that you can plot that shows how these computers have changed over the years. This is a huge simplification in this graph, but it shows an important point. Up until the mid-2000s, the main difference as these computers got faster and faster and faster was the fact that the cores, the processors, the CPUs in your computer were just getting faster year on year. But that sort of has come to a halt now. And what we're seeing is that clock speeds on processors, as you'll see even in desktops and laptops, is no longer going up. And what we're now seeing instead is an increase in both the number of CPUs in the very big supercomputers and also the number of cores that you have in a single CPU. So this has implications for the way that you write your software. So I talked about Exascale. What are the biggest challenges for us? The biggest issue that we face is one to do with power consumption. As you try to do more and more calculations with your CPUs, the power consumed goes up at a very fast rate. And so these huge supercomputers are using vast amounts of power. It's now the cost of running these machines over their lifetimes will outweigh the cost of buying the machines and install them. In some cases, several times. So one of the most important costs with a supercomputer is just having the power to run it and to keep it cool. Because you also, if it's whether it's liquid cooled or air cooled, you still have to power the machinery that cools the machine rooms that these computers run in. So there's a sort of hard limit, pretty much, of about 20 megawatts that's generally assumed as the value as to which it becomes completely unreasonable to provide more power to a supercomputer. Computers like Hector, the national supercomputer that we run from here in Edinburgh, already have their own power substation. You can't just plug them into the wall. They consume vast amounts of power. So trying to make hardware that deals with these problems with power, so it can do the computations faster without consuming more and more power, is becoming much more important. The other big thing from the last graph, we saw that the number of processors and the number of cores were rising all the time. As you have more and more cores in a computer, and to reach the exascale, incidentally, out in about 2020, as it was shown in that first graph, it will be quite likely that we will need tens of millions of cores. If you have tens of millions of cores in your supercomputer, the chances of one of them failing in the course of running your job is actually quite high. So they talk about a mean time between failure, the MTBF, is the sort of typical time it might be before one of the cores in your machine stops working for one reason or another. And for these large supercomputers, when you have tens of millions of cores, this looks like it's going to be measured in minutes or hours and not days. So the computers of the near future are going to have to be cleverer about the way they deal with failures within the machine. And the other factor in approaching exascale, as I mentioned, the number of cores is going to increase. So it'll be quite likely that the programs to exploit these large supercomputers will require typically billion-way parallelism. You're going to have possibly a billion processes working in parallel to try to solve the problems that are running on these machines. There are side effects of this as well, in that the memories of the machines are not growing at the same rate, so the memory that you have available per core is significantly reduced. And the kind of runtimes that we have available at the moment to deal with this parallel programming, things like MPI, which you'll learn a lot about on the course, may not continue to scale up to this level and give you the performance that you need to deal with this many processes. So these are problems. The power is more of a hardware problem, and sort of as we go down to dealing with a number of cores, this becomes very much a software problem. Who deals with the reliability is a hotly contested question. It's a difficult one to deal with, and I think a lot of people, the software people, often think, well, it's up to the hardware people to sort out, and the hardware people think it's up to the software people to sort out. But either way, they're going to have to work together to work out how to write programs that work efficiently on the computers of tomorrow. And that's another sort of theme of what we do in the MSc here. Although it's very much about software, writing programs, and it's not in detail about the hardware of the machines, you will need to understand the hardware of the machines to understand how to write good software. So we do go into some detail about the hardware in these variety of computers as you go through the course. This next slide shows some of the drivers for high-performance computing, and this is where the smartphone bit in my title comes in. I've actually got a tablet drawn here in the top left-hand corner, but the idea is exactly the same. The supercomputing market, these top 500 supercomputers in the world, are actually, it's not a very big market in terms of computers as a whole, and in these days consumer devices like phones and tablets. And actually, probably what the supercomputers of tomorrow are going to be made out of will be commodity components, or components whose design has been influenced by those that come from commercial and consumer devices. So we talked about the power problem being a problem when you have to run a supercomputer that's so big. Where this is being addressed in the consumer market is in mobile devices, because we're all very concerned about the battery life of our phones and tablets, and so there's been a lot of work that's gone into making processors and other components that work very well at low power. So things like the ARM processors that you might find in an iPhone or another kind of smartphone. These are a different architecture of processor, and there are people now who are thinking about building the possibility of building supercomputers out of these same ARM processors that you might find in mobile phones. What has driven the multi-core revolution, really, to some extent, and the amount of floating point operations that you can do within a single processor has probably been driven to a large extent by desktop machines, by gamers who make great use of the processors in their computers, and particularly those who want the latest and greatest graphics, because this has driven the technologies behind GPUs a lot over recent years. And GPUs are really, on a single chip, lots of low or lots of very simple cores that are designed for doing graphics calculations. But actually, graphics calculations are quite similar to a lot of the mathematical calculations that you want to do in scientific applications. So you can use a GPU to do a lot of floating point operations, a lot of arithmetic operations in a very short amount of time, and that's again something you'll learn more about on the MSc. So then we have the system software. What actually runs, what's the operating system on these biggest supercomputers in the world? Well, with a few exceptions, but not very many exceptions, the answer is Linux. And again, this is being driven by commercial clusters and to some extent of what people at home and in universities are running on their machines. So a lot of the ideas behind the operating systems, again, are coming from consumer and commercial devices. Compilers, I don't know quite why there's a Windows logo below this. This is a slide that I've borrowed from somebody else. I think the idea is also to say that, again, the compilers that we use on supercomputers, with a few exceptions, are often the same compilers that you would use to write desktop software. So a lot of the compiler technologies have been developed and incorporated into the consumer products, and then further down the line they get used by the supercomputers. The last thing on this slide is the interconnects, and this is one of the few things that isn't really used in most other consumer technology or commercial systems. It's what really makes the difference between a cluster and a supercomputer. And it's not the bandwidth of the network connections between the components that matters, it's the latency, the time it takes to set up and send a message between two processors. And it's the interconnects that until recently have been quite bespoke pieces of equipment, either specialist networks designed for supercomputers or made by the vendors themselves, like Cray. The Cray supercomputers, like Hector, the one we have here, has its own custom interconnect, which is designed to link up all the processors in the machine in a very efficient manner. And that's really the factor that turns lots of independent processors into a supercomputer. But the fact that you've got all of these consumer technologies feeding into high-performance computing also means that a lot of the ideas that you will learn as you go through this MSc, although it's targeting high-performance computing and supercomputing, will be equally relevant and becoming more and more relevant whether you're programming for a desktop machine or a mobile phone, because it's widely predicted that the next iPhone, for example, is going to have a dual-core processor. There are already phones with more than one processor in, and your laptop and desktop will almost certainly already have more than one processor in. So to use these machines to their full capability at the moment for a single program, you already have to do parallel computing, and that's something that you will learn all about on the MSc. So this is a picture of Hector. This is the UK national supercomputer that we have here in Edinburgh. You'll all be getting accounts on this machine, so you'll all have a chance to run on one of the fastest machines in the world, and the fastest machine in, actually I don't know if it's the fastest machine in the UK now. Some of the Blue Gene queues might have just picked it at the post in the last top 500, but it's the last, the biggest computer available for general scientific research in all different fields. And you can see that Hector has 90,000 cores. So I mentioned a little bit about GPUs. This is just another thing that we're interested here at EPCC, and something you'll learn a little bit about on the MSc, the idea of accelerators and coprocessors. So this is an area that's important to exascale computing. This is one of the ways that we think we will get further up that dotted line to be able to make computers that can do that 10 million billion calculations per second. It's quite possible that these computers will make use of GPUs very similar to those that you would get in a gaming desktop PC. So these GPUs already have of the order of 1,000 simple cores in a single die. They've got very high memory bandwidth, which is also a very good feature for being able to write high performance programs. But they do still require a CPU as a host, so you can't run your operating system or indeed your entire program on the GPU. They have to act as an add-on, a coprocessor, or sometimes called an accelerator, that will work alongside the CPUs. Intel has been developing another thing that they call a coprocessor. Its code name was Mike. I think it now has an official product name. I don't know, was it successor to Sandy Bridge? I think it might be Knightsbridge or one of these. But they're branding it alongside their Xeon processors, so it won't be called Mike when it comes to market. But this is already on a single processor. They're looking at having of the order of 100 cores on a single processor. And this is actually very similar architecture in a lot of ways to the shared memory computers as a whole that we were working with not too long ago. So it really is a 100-core shared memory processor on a single chip, and the only way to make the most of that chip is to write programs that can run with at least 100-way parallelism. So these are new technologies that are just breaking through, and you'll learn about the best ways to program some of these as part of the course. And here's my last slide for today. It's just an example of some of the projects that are going on in Europe to prepare for Exascale at the moment. There are 3 big projects that have been funded by the European Union. We're involved in the last one, called Presta. The first one, Deep, is about making a prototype for the Exascale machine. And what it does is it takes a load of CPUs, a load of processors, a load of GPUs, the graphics processors, and instead of connecting them through the kind of bus that you would get in a desktop machine or whatever, it connects them directly through InfiniBand, which is the same kind of interconnect that you would get on some kind of supercomputers. So they're taking a group of CPUs and a group of GPUs and trying to connect them all on one big InfiniBand network. So that's their approach. Then there's the Mont Blanc project, and this is working with the ARM processors that I mentioned, the exact same architecture of processor that you get in your smartphone. So the idea is that they're trying to build this exascale computer out of the ARM processors. The project we're involved in here at Cresta doesn't have any hardware drawn on the right-hand side there. Instead, it has a list of applications. So this the Cresta project is very much about the software, and it's very much about the fact that we know that the kind of codes that are running on existing computers will not perform well on either of the two above when we go to exascale. So there's a lot of work to be done in terms of writing, changing the ways you write parallel programs, how you write high-performance programs, so that they can make use of the hardware. And that, again, is very much the idea behind our MSc. It's about writing software that can really make the most of the leading computers, the leading supercomputers, and the leading processor hardware of today. So hopefully that gives you a little flavor of of where we are, some of the things that EPCC is interested in at the moment, and ties it back to some of the things that you'll be learning about on the MSc.